Okay, hello. We are continuing with chapter 2, and remember, we're focusing on descriptive statistics. So, everything we're describing, or everything that we're going over in this chapter, involves how to describe a data set. And so, this is, of course, our two main categories are descriptive versus inferential. And so I know that we have been covering material in a very fast pace. However, trust me, you will be grateful because as a result, we're going to be able to spend more time for the inferential. And that's usually more difficult for students than the descriptive part. And so that's why I'm pushing us really in the beginning to get through these first few chapters on descriptive statistics so that we're not as rushed for the inferential, and we can take our time and go through inferential very carefully. Okay, all right. So we are now on section 2.5, and we're going to be talking about measures of position. Measures of position. So we're going to be learning or working on 3 objectives. The first is going to be an objective about quartiles. Quartiles go hand in hand with box and whisker plots. We talked about quartiles in class when you do your 1-var stats. You have access to some information that gives you Q1, mid, Q3. And so this portion right here, this is what this stands for. First quartile, second quartile, third quartile. Okay. So the second thing we're going to work on is how to interpret other fractiles. So notice that we've got our root or our suffix here is "ile," right? So quartile, fractile. So we'll have percentile. Instead of taking your data set and splitting it into 4 for quarter, right? Quarter is 4. For percent, you're going to be splitting it into 100 different groups. Okay. So we'll talk a little bit about those. And lastly, we will determine and interpret the Z-score. So this is our first introduction to Z-scores. Z-scores, believe me, by the end of the semester, you'll be very, very familiar with Z-scores. We're going to use them throughout the entire semester. So we're getting our first look at Z-scores right now. Okay. Get out. Get out. Okay. All right. So let's talk about quartiles. So, in general, a fractile is any number that parts or divides an ordered data set into equal parts, right? Quartiles are the parts if you take your data set and you split it into 4 equal parts. So if you take your data set and split it into 4 equal parts, those parts are called, you have 4 quartiles. Let me write that down. And you have 4 quartiles. Okay? If you take your data set and you split it up into percentiles, then you've got 100 percentiles. So your data set is split into 100 percentiles. Your data set is split into 4 quartiles. You kind of get the idea here. Now the quartiles are labeled as such. Your first quartile is Q1, and about 1/4 of the data fall on or below Q1. Your second quartile is Q2. Notice that Q2 is the same thing as the median. So I'm going to put that here. Q2 is the same thing as the median, because the median, remember, the median in the data set takes your data and splits it into 2 equal parts. So your second quartile is going to do exactly that. About half of the data falls on or below Q2. And the third quartile, Q3, about 3/4 of the data fall on or below Q3. And we're going to do some examples which explain what these terms mean because a picture is worth 1,000 words. So let's do this example right here. So the number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed. Find the first, second, and third quartiles of the data set. Okay, so we've got our data set, and the first thing we need to do is we need to arrange the data in increasing order. So the first thing you're going to do, first thing you're going to do, so step 1 is going to be to arrange the data in increasing order. Okay, so for us, with this data, I need to find...
It's 22 hours.
Thank you. It's 10 o'clock. Thank you. Okay, so I'm going to start off with, it looks like 6 is the lowest. So I've got 6, and then I've got 7. I've got an 8, 9. Okay, I've got a 10. Excuse me. Okay, I've got an 11. Next one appears to be a 15. Then an 18. No, 17. 17, then 18, then 19. Then 20. Ooh, no, I've got 2 18s. So let me change this to an 18. 19, 20. 31, 54, 59, and a 104. Okay, so to arrange the data in increasing order, here we go. And let's just count to, well, we don't need to count to make sure that we got everybody, all of the data points, because we put this little dot on top of each one. All right, so that's the first step. The second step is now split the data in half. Okay, when we say split the data in half, here's what we mean. If I've got 15 data entries, then I can think of it like this. 15 over 2 would be 7.5. So I can go in 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Aha, so 18. This is my middle. Okay. So I've split the data in half. So notice half of the data is below 18. Half of the data is above 18. Okay. Now I'm going to repeat this, and I'm going to split each of my halves in half. So split each half in half. So I found out so far that 18 is equal to Q2. Because remember, what is Q2? Q2, about 1/2 of the data fall on or below Q2. Q2 is the median. Now I'm going to find the first quartile. Okay, so about 1/4 of the data fall on or below Q1. All right, so my first, do you see how I've got this first, I'm trying try to use a different color. So this is the first half of my data, and I'm going to split this in half. Now, how do I split in half? Well, I need to know how many points do I have. 1, 2, 3, 4, 5, 6, 7. So if I split in half, this is going to be the half. In the middle there is Q3. And then lastly, you take your bottom half. That wasn't a good split, but you split your bottom half in half into a top and a bottom. And now we've got essentially 4 equal parts. And so that is Q1. Okay. And again, these are estimates. So going back, notice how it says in our definition that we're working with about a half, about 3/4, about 1/4. Okay. Because you might have a data set that doesn't split evenly into 4 groups. So that's why these are, in some sense, estimates. So we've got Q1, we've got Q2. Now, the last thing I need to do is figure out Q3, which is I need to take the top half of my data set and find the median of the top half. And that looks like 31. Okay. So this is my Q3. Okay, so find the first, second, and third quartiles of the data set. Q1 is equal to 10. Q2, which is equal to the median, is equal to 18. And Q3 is equal to 31. So you can also find the Q1, Q2, Q3 using your 1var stats. So don't forget about 1var stats. Okay, so I'm going to say don't forget about 1var stats. Oh, I guess I should have written the answer on that page. All right, never mind. Here we go. Remember how we gave our measures of spread? So I'm going to put here recall. Measures of spread. Our first measure was range, and we said range is equal to max minus min. And this was our first formula. Right? Now we're going to have a new formula to add. This new formula is the interquartile range. Okay, and it is abbreviated IQR. So the interquartile range gives you, the formula is Q3 minus Q1, and the interquartile range tells you the spread. So IQR tells us the spread of the data about the median. So if your IQR is small, that means that your numbers are really close to each other. If your IQR is large, that means that your numbers are spread out. Okay, so let's do an example. Find the IQR of the data set. And this is going back to that example that we had back here. So we know that Q1, they've given us the formula here. They've given us the formula Q1 is equal to 10, Q2 is 18, and Q3 is equal to 31. So the solution is quite simple. RQR is equal to Q3 minus Q1. So that's just going to be 31 minus 10, which is equal to 21. So IQR is a number, just like the range is a number. The interquartile range is a number. Okay, now let's talk about box and whisker plot. A box and whisker plot allows us to visualize. So it allows us to visualize the properties of a distribution. So we'll say the spread of a distribution. The spread of the distribution with respect to the median. Okay. So you use the box and whisker plot as an exploratory data analysis tool. What does that mean for it to be an exploratory data analysis tool? That means that you use the box and whisker plot to find out what questions you need to ask. Okay, so it's a way to explore your data to see, oh, do I need to look more into this? Do I have outliers? It's very easy to see outliers with a box and whisker plot. Okay, so that's what we mean by an exploratory data analysis tool. Now, in order to create your box and whisker plot, you're going to need your 5-number summary. And I would like to point out that your 5-number summary is, so this is a phrase that's used a lot, 5-number summary. We get our 5-number summary quite easily on the calculator. So remember, you'll have your min, Q1, and it'll say med for median, Q3, and max. This forms your 5-number summary. Okay, and so we've got some information here, and I'll let you read that. You can pause the video and read this in order to construct in order to draw a box and whisker plot. First, you find your 5-number summary. Then you're going to draw your horizontal scale. The scale needs to be as long as the range of the data, and this range is referring to the interval range. Okay, so let me just get to it. I'll show you how to do it. Okay, so draw a box and whisker plot that represents the 15 data set. We're still working with the same data set. So here, this is my 5-number summary. So I've already got the first step down. So what I'm going to do is I'm going to draw I'm going to draw my axis here. Now, this point right here is my min. So let me write that. This is my min. This point here is my max. This is my max. So if I had to put numbers, so this is a 6. So kind of I'm going to draw a number line below it. Okay. So imagine this is 6. And then our max is 104. So if this is 6 and this is 104, then about halfway this is like maybe 55. So let's see. I think I'm actually going to draw it a different way. So because I don't think this is as intuitive. So sorry about this. Here's what we do. We're really going to, you start off drawing your, and let me not do that in fuchsia. That's not a good color. Do it in black. You start off drawing your axis. Okay, so you just draw your axis. And now I'm just going to number it. So I'm seeing here that my min is 6 and my max is 104. So I need to get up to let's just say 110. And I'm going to start at 0. And now what I'm going to do is I'm just going to go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90. This is 100. I change that to 100. And then one more for 110. Okay, now that I've got my scale, it'll be easier for me to draw. So here we go. So I'm going to put my min at 6. So that looks like a good estimation for 6. My max is at 104. So that looks like a good estimation for 104. And I'm going to draw.
It's 2250.
My line in between them. Okay. Now I'm going to draw a line segments that are perpendicular at Q2. So for Q2 is equal to 18. So I'm going to go over here to 18. And I'm going to have my line segment. And I'm trying to make it very thick. I don't know if you can tell, okay? Because the median should be a very thick line. That's Q2. Q1 is 10, so I'm going to make a thin line there. Q3 is 31, so I'm going to make a thin line there. Okay, and now I'm going to make these meet. Okay, so let me even this up now. Okay, so you end up with a box. I'm going to go back and make my median the thickest line. Okay, so now let's label this. So this is my min. Your first arrow here is Q1. That middle line, which is thick, is Q2, which is the same as your median. This line here is Q3. And this last one here is your max. So your whisker, this is your whisker, and this is your whisker. And so you've got a box, and you've got whiskers. And so already you can tell just from looking at this, you can get an idea of the spread of the data. So, for instance, if we were to try to draw, if we were to try to maybe draw a histogram that corresponds to this data, this, do you see how long this is? This means we're going to have a right tail. So we'd have a right tail, a right tail distribution, because we've got this long part. This is a long tail right here. Okay, so the data is bunched up over here because remember, 25% of the data is between 6 and 10. 25% of the data is in here. 25% of the data is in here. And then 25% of the data is spread out here. So this is going to be our tail. All right. So now let's talk about percentiles and other fractiles. So far, we've been looking at quartiles, which is essentially taking your data, you arrange it first, and then you split it up into groups of 4, right? And when we say split up into groups of 4, we want there to be the same number of points in here. So like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So that's quartiles. Now for percentiles, you're going to take your data and you're going to split it up into 100 different groups. Okay, so quartiles divides the data into 4 equal parts. Deciles divides the data into 10 equal parts, because remember if we remember our root terms, deci is for 10, like decimal. I don't know if you remember, but decimate. You know, if you say, oh, the population was decimated, it literally means that the population was reduced to a tenth of the size it originally was. So, you know, back in the day, they would talk about armies decimating each other. What that means is that this army came in and like eliminated 90% of, you know, the other army. All right. And then lastly, percentiles. And we're actually used to saying percentiles because imagine how many times you might say, oh, are you in the top 10% of your class? Right? What that means is line up everybody in your class, maybe according to GPAs, right? And then top 10% means that your scores or your GPA is better than 90%, right? So 90% of the students have GPAs lower than yours. That means you're in the top 10%, right? You could say, are you in the top 1%? That means your score is higher than 99% of the other people, okay? All right, so let's look at this example here, interpreting percentiles. The ogive represents, now if you don't remember what an ogive is, Go back and look at section 2.2. So this is from 2.2, and I'll just put and 2.1 because they kind of go together. I think actually it's maybe 2.1, but you get the idea. So ogive, you want to be familiar with these terms. The ogive represents the cumulative frequency distribution for SAT scores of college-bound students in a recent year. What test score represents the 62nd percentile? How should you interpret this? Okay. Well, we know we want the 62nd percentile. So let's look up here. We're going to look at our graph over here, and we're going to just estimate that 62 is here. So now, let's see, how far over? Okay, it looks like this is the score. This is a score corresponding to the 62nd percentile. So let's see if we can try to estimate what the score is. It's kind of hard. So let's say if that's 600, and that's 900, and that's 1200. It looks like this is skipping by one, like 700, 800, 900, 1000, 1100, 1200, 13, 14, 15, 16, 17. So maybe 1695, maybe. So let's estimate 1695. Right? Maybe we're a little off because our line is crooked, but 1695 is the 62nd percentile. And what that means is that 62% of students scored less than 1695. So 62% of students scored below 1695. Okay. All right. Okay, so our sketch was a little off. Apparently, it is exactly 1600. But still, the interpretation is valid. So this means that 62% of the students had an SAT score of 1600 or less. Okay. Now, the last thing is let's get to the Z-score. This is very exciting for us because this is our first step into college level statistics, is what I'll say. So for the standard Z-score, the Z-score represents the number of standard deviations a given value falls from the mean. So let me just kind of explain what this is. So imagine, here's your mean. So maybe you're right skewed. Maybe your distribution is right skewed. Okay? And suppose this is your mean. Now, we could look at mu plus sigma. Anything in here, any value in here is within one standard deviation above the mean. Okay? Now let's go out and we can go 2 standard deviations above the mean. That means we're looking anything in this entire region. So if you were to say all of the values, what are the values within 2 standard deviations of the mean? Here's how we interpret it. We could be going above or below, right? So mu minus sigma, and then mu minus 2 sigma. And then we would say any value in between mu minus 2 sigma and mu plus 2 sigma is a value that is within 2 standard deviations of the mean. So you kind of think, what's the distance, right? So the distance from here to here is sigma, which is sigma. Remember, sigma stands for standard deviation, right? Population standard deviation, sigma. How far is it from here to here? 2 standard deviations, okay? So our distance is 2 standard deviations this way, 1 standard deviation. You could be above or below the mean, okay? And now we've got our formula for the z-score. So suppose you had a point x. So suppose maybe this is x, right? You could find the z-score for x. And how you find the z-score is you calculate the value, which is x, minus the mean, divided by standard deviation. Then z is going to tell you how many standard deviations away from the mean x is. So let's just put here note. If z is positive, then x is above the mean. Okay, that reminds me of a movie called Above the Rim. That's not what we're talking about. We're talking about above the mean. Okay, so if z is positive, then x is above the mean. If z is negative, x is below the mean. And what does it mean to say it's above the mean? This means x is greater than. So it's the same thing. Okay? If z is negative, then x is below the mean. And if z equals 0, then x has to be equal to the mean. Because look at our formula. The only way z is equal to 0 is if the numerator is equal to 0, which means x is equal to mu. Okay? So if z is equal to 0, then x is the mean. If z is less than 0, if z is a negative number, x is below the mean. And if z is a positive number, x is above the mean. All right, let's look at this example here. So it says, in 2009, Heath Ledger won the Oscar for Best Supporting Actor at age 29 for his role in the movie The Dark Knight. Okay. Penelope Cruz won the Oscar for Best Supporting Actress at age 34 for her role in Vicky Cristina Barcelona. Now, here's the issue. The question is, even though Heath Ledger was 29, the average age for men to win the Oscar for Best Supporting Actor is 49.5, right? For Penelope Cruz, she was 34, but the average age is 39. So do you see how typically, if we go by the mean age for females to win the Oscar is less than the mean age for males. So in other words, typically, females that win the Oscar, if you're going to win the Oscar and you're female for best supporting role, you're going to be younger than males that win. Okay? So the question is, even though Penelope Cruz is 34, which is a little older than 29, it's hard to compare. It's hard to say, was Penelope Cruz young versus Heath Ledger, because they're different categories. So it's kind of like you're comparing apples and oranges. Here's where the z-score comes into play. So the z-score is really beneficial because the whole purpose of the z-score is to even out the score, right? So it's a way to allow you to compare distributions and to compare data,
It's 22:30.
when the data have different means. Okay? So, for instance, if we were to kind of try to draw, what does it look like, a distribution of all of the people, all of the males who have won the Oscar for Best Supporting Actor, right? I don't know, some of them So apparently the mean is 49.5. So here's 49.5. So, and then maybe the distribution is like that. Okay. So some actors are older than 49.5 and they win the Oscar. Some actors are really young, but it's typical for them to win at 49.5. And then over here, we've got actress. But now notice, in fact, let me do actress in a different color. So for actress, which I'm going to do in green, we would have 39.9 as our mean, okay? And so if we had something like this, you see it's hard to compare. It's just hard to compare. It's hard to see. It's hard to compare because it's like you're comparing apples and oranges because the distributions have different means. Okay, so let's write down. So we're going to try to answer our question here. And the question that's asked is to find the z-score. Find the z-score that corresponds to the ages of Ledger and Cruz. Then compare your results. Okay, so let's remember our formula for the z-score. The z-score is equal to the value minus the mean over the standard deviation. And in fact, I can write this. Copy. Paste. Okay, so that we can just actually save this space because we're going to use the same formula for Heath and Penelope. Okay, so for us, Z is going to be, what is our value for Heath Ledger? Well, how old was he when he won? Heath Ledger was 29. So Heath Ledger was 29. What is the mean? The mean for actors is 49.5. So minus 49.5 over the standard deviation. They have to give us the standard deviation. Standard deviation for, so let's see here. So the mean age for Best Supporting Actor winners is 49.5 with a standard deviation of 13.8. So over 13.8. And now what is that? What is 29 minus 49.5 divided by 13.8? That is negative 1.4855. Okay, so Heath Ledger's age is about 1.5 standard deviations below the mean. Okay, so that's about 1.5 standard deviations below the mean. And on the other hand, let's calculate for Penelope. So for Penelope, let's see, her value is 34. Her mean is 39.9. So let's do 34 minus 39.9. And then we need divided by the standard deviation. Standard deviation of 14. Okay, so we need 34 minus 39.9 divided by 14, which is equal to negative 0.4214. Okay, so we would say that this is about half a deviation, half a standard deviation below the mean. Okay, so how do we compare the two? Well, they both are relatively young because they're both below the mean, right? So they're both are relatively young because they're both below the mean. However, Heath Ledger is younger, in a sense, than Penelope Cruz because Heath Ledger is further away from the mean. Okay? And then overall, as we remember from our empirical rule, remember our empirical rule? The empirical rule states that, well, actually, we're not using the empirical rule here. Well, kind of. The empirical rule gives us an idea of which scores are usual, which scores are unusual, and which scores are very unusual. So, since both of the z-scores are in this zone here of usual scores, right? So usual z-scores, since both of the scores are usual, okay? So they're young, they're relatively young, but it's not extreme. Do you see what I'm saying? If you had an age where someone was 3 years old, that would be very extreme because there'd be many standard deviations below the mean, okay? So compared with other Best Supporting Actor winners, Heath Ledger was relatively younger, whereas the age of Penelope Cruz was only slightly lower than the average age of other Best Supporting Actress winners. Okay. All right. That's it. Thank you.